Okay, so what we want to very briefly cover today in our presentation is a few things about classic models and AI models, especially around advantages and disadvantages. Also some data requirements and what we would like to see in the data. Then Craig will take over with the exciting bits with the new developments in AI, and Richard will close the floor with the data sets and things we are doing and some of the projects we have now. So next slide, please. So I will start with the classic models. We start with the basic, with what we know. I will talk about these models at a very basic level, just so I can understand it. So what the classic models do, they in very simple terms, they pair variance in the dependent variable that we are interested in with variance seen in the input variables. And they have some advantages. If we have perfect data, and we'll come back to that later, they are very strong and straightforward. And a very good point about them, they expose the coefficients for each selected variable, so you can understand how the variable contribute to the result of the model. They also expose the decision processes for variable inclusion, exclusion, and you can also interrogate and work with those limits to choose your inclusion levels and so on. And these things are still good because we will see there can be problems in the data that we cannot see. But they also have a lot of disadvantages that we all met in our career. So one of it, which is not the worst case scenario, but what can be paired, is assigned to a constant. So you start from a level, but you don't know why you start from that level. Then especially in more difficult situations, the models that we get do not fit best for the actual situation. Also, these classic models, they work with user-defined limitation in assumption. So if we work with count data, then we tend to work with the logarithmic models, for instance, which is already a limitation to the model. And another quite big disadvantage, especially when you want to apply things in real life, is that sometimes this model pair the effects wrongly to other variables, which might be collinear, codependent, whatever, with some missing data or information. And we'll see that a few slides further. Next slide, please. What do AI models do? They do the same thing. They also pair variance in the dependent variable with variance in the input variable. They usually exhibit better results than classic models, as much as we could see around us until now. They find the best fit without preset limitation, and they can change their settings every step. So they will give us a best fit. And they allow for a lot more interaction between input variables inside the models, which sometimes with classic models, it's a bit harder to actually be done. But they also have these disadvantages. First, they do not expose coefficients or the decision processes. So we know what is happening, but we don't know why. We don't know what it's influencing, why we're getting those numbers. Then it's more difficult to interrogate. And therefore, you can't, if you don't see the variables, you don't see the processes, you can't interrogate too much, then you might miss some warnings that the classic models do give us. But also, these models with the same data also sometimes assign effect wrongly to other variables. It's just we are not able to see it. Next, please. So very briefly, if those are the data points, the yellow points are the data points, then an ideal function would be the green line. And on the left side, we can see how classic model we would expect to approximate that line, and how an AI model is able to have different steps and change the functions they use. So it will be a better approximation. Next, please. And here is one of the cases where we actually met in reality with the problem that I was underlining, that some of the effect might be assigned wrongly. So here is an example with just a selection of variables from an exercise from a project we had with TfL in London, where I will say we, but mostly was Craig, so you can catch him for a lot more questions. We used GLM modeling, but also GLM is generalized linear model, and also artificial neural network for modeling the same elements to understand predicted risk. So you can see here that we have for average speed, when the average speed increases, the risk increases everywhere in all the calculated columns. But also, which is for someone who works in the area, which is unlikely to be true, if you have 20 miles per hour limit roads, as opposed to 30 miles per hour or more, you will still have an increased risk, which can't be true, because we just find out that actually increasing the speed, it's increasing the risk. So decreasing the speed means decreasing the risk. So which means that the 20 miles per hour limit data that we had probably covers for something we can think maybe about pedestrian flows, maybe about behavior. Maybe people perceive 20 miles per hour being safer, so then they act more risky. So with the GLM, you can see that. You can see individual variables contribution in the model, and you can spot where maybe it's a warning that you might need more data. With an INN, you can get better, more accurate prediction, but you can't understand why, which variable is influencing the model, and in what way. And this is really important. Now I'm going to just talk very briefly about data requirements. So these models need data. What we would like, let's say ideally, to have in the data, but of course, we want to have relevant data, because yeah, we might have a lot of data. If it's not relevant for the element we're investigating, we shouldn't put it in. We want the data to be reliable, to have an appropriate granularity, to be clean of systematic errors and other errors. But very important, we want the data, ideally, we want the data to cover a full picture of variables that could exhibit influence on the dependent variable. For instance, in most of the models available now, and in most of the projects we look at, there's very scarce data on driver characteristics, which do we consider that is not important enough? Myself, I consider that it is. So I think for both classic models and AI models, the following is valid. If we don't have perfect data, garbage in, garbage out. So we need to understand that data and quality of data is very important for both models, and none of the models will actually be able to fix that. And classic models will allow us sometimes to spot out problems, whereas AI might cover that through better fitting. So we need to be very careful. If we want to switch from classic to AI, we need to take this risk in consideration. Next, please. So as I was saying, until we are sure that the data fulfilled the mentioned requirements and probably some more at the minimum acceptable level, AI, I don't think myself and probably my colleagues will agree that we should use AI in isolation as a better solution, but better to use it together with classic model to get better prediction, but make sure that we don't miss important problems. So data is still the holy grail. And we think the first use of AI should come to improve the data quality, quantity, and availability. And once we have those better, we can start using AI together with classic models to improve predictions. And Craig will explain about developments in this area.
Yeah,
thank you.
Thanks, George. Yeah, so George has touched on some important points there. Yeah, so mainly that we are using increasingly AI to make real world decisions, and just naturally AI has this black box nature, which means there really is a demand for explainability of the model if you're going to make real world decisions that not only impact on sort of financial things, but also on people's lives. There is a need for explainability, but fortunately, there have been sort of leaps and bounds in this area recently. So model agnostic AI, explainable AI, is becoming more and more possible, but more importantly, it's becoming more accessible. So there are increasing number of packages available in R, Python, a series of programming languages that pair with the same software that people are using to build their models in order to provide some sort of explainability. And this is then bridging the gap between the two very important things George was saying, where you've got this really accurate AI modeling, but it's really sort of difficult to interpret, whereas these classical models have these coefficients that you can interrogate, and really we need to make the best of both worlds here. So I'm just going to touch on a few of these techniques. So yeah, one of the best ways of doing this is to build sort of local approximations to complex models. So what you do is you take your big AI model, whether it's a neural network or something slightly easier to build. What you do is you look at specific data points and you build a smaller model around that data point that is more explainable. So this can be done either by taking a specific data point and looking at how the model reacts to perturbations in a neighborhood around that data point, and then use those results to build small local linear models, or slightly more sort of theoretically beautiful Shapley values from game theory can provide axiomatic ways of defining sort of local contributions of models. And what this does is, at least locally, it allows you to build these coefficients that you'd see in your classical sort of GLMs, but at specific data points using your neural networks or your random forests or whatever complex AI model you're planning to use. So this really does allow you to say, you know, if, for example, you've got a model that's predicting risk, which of your input variables are contributing to what, to whether it's high risk or low risk, or if you're using AI to determine whether there's, for example, a lamppost or a bollard in an image, you know, which parts of the image are contributing to that prediction. And this is really important. But again, this is all very local. This is around specific data points. This is around sort of specific areas in the road network if you're looking at risk modeling, or it's looking at specific images if you're looking at sort of image segmentation. Next slide, please. But there are also global explanations of models, and I think it's really important to look at both. So not only do you need to explain, you know, why individual decisions are being made, you also need to be able to say whether your model is actually doing any good on the whole. So the simplest way of doing this is building a global surrogate, a simpler version of the model to sort of sit alongside the real model. Something George touched upon, using sort of these classical models alongside AI models. But you can also interrogate your model, so you can look at feature importance. So what happens if you drop or permute or just generally change specific input variables? There are statistics to look at feature interactions. Just generally, there are a huge number of different ways of looking at explanations of models, and I'm just touching on a few here, but I think the importance is that these things do exist and are often overlooked.
Okay, thank you, Craig. My slides are going to be a little bit different. I'm not the professor in the room, certainly, but what I am and always have been is somebody who's obsessed with getting more data, and hopefully that data isn't garbage. So I am the cookie monster of data. I want more data all the time, because ultimately I think that the more data that I have, the more I can find out. And when you're looking at big data, that can be an enormous amount of it. So one area that I've been looking at particularly is around telematics data. So I'm calling it telematics. It's got various other titles, floating point vehicle data. But if we think about the information that's available in vehicles, I think this could be incredibly useful for many of us if we can get access to it. And there are 3 different types of data that you can have access to. So there's the GPS data that I'm sure many of you are familiar with and have used, sensor data, which you may have done, including information on the driver activity, acceleration, braking, cornering, other vehicle features that are being used, and then also potentially vehicle diagnostics. I'm thinking a little bit here around post-collision investigation of, the moments just before an incident took place, something that may be of relevance to collision investigators. So I'm going to take you through some of the examples that we've got that are hopefully really straightforward and easy to understand. So here is a map. And this is a map that simply shows vehicle speeds versus this posted speed limit. So wherever we have the blue roads, this is my hometown in Northamptonshire in the UK, wherever you see the red limits or the orange limits, this is where we're seeing over speeding events. So you can see just to the side here, if I zoom in and we show some of the details on there, this is the kind of information that we have. And this is showing overspeeding that's in a 20-mile-per-hour limit, so a 30 km/h limit. And one of the only ones available in this town, normally the rest of them are 30 miles per hour limits. And you can see the level of speeding events that take place according to the direction of travel of the vehicle at different times of day and either average speed or 85th percentile speed. And we're producing this in a tool that's being used by local authorities and enforcement agencies to help target where to carry out enforcement activity. So it's really easy for any police officer to look at this and instantly see where they should be carrying out their road safety work. We can also use it to have a look at vehicle flow data. So getting hold of accurate vehicle flow data normally requires a lot of expense because you have to put out sensors or surveys or things like that. It is possible to model data using telematics vehicle floating point information. So you can see on here that the darker color roads are the ones that have the most amount of traffic on them. So, it doesn't require an enormous amount of the fleet to be covered. Typically 3 to 6% of the fleet is enough for you to give accurate estimates of where traffic flow is highest. And because I know these roads, I can see that these are the main distributor roads, and that is indeed where we see most of the traffic. The grey areas that you get on there are the ones that don't have that. And because we've got this broken down by time of day, we can see where congestion is highest as well. Remember, we got those different time zones before. So wherever you see the darker purple areas, that's where the most congestion is, and the green ones are where the most free-flowing data is. So imagine if you could have this for the whole of your road network. And as I said, we provide this to road authorities, so they really need applied use of this data. A quick one here is on harsh braking, something that we talked about quite a lot yesterday. So here is some vehicle telematics data from a large transport fleet that we've worked with that looks at incidents of hard braking across the central area of the UK, so around Birmingham. This in itself doesn't tell us a lot because these are simply the roads that are travelled on more frequently. You need to think about how you can relate the harsh braking and other data together. So what we do here is that we create an index. So you can see that those roads are coloured according to the level of harsh braking based on the amount of vehicle traffic that's going along them. Trying to help put that into context. And that's just harsh braking. You can see that we've got collisions, near collisions, following distance problems, late response, drowsy, all these other kinds of data sets that are being collected but are not regularly being used and tend to be held in data silos, often by private companies. So the question that I always ask is, what metrics do we know cause higher risk? And are they road risks or user risks? And I'm sure we're going to be getting onto this in a lot of the conversations later on. So we've talked about harsh braking, and the opposite of that almost, which is swift acceleration. How about unusual cornering speed? And I've spoken to telematics analysts who said that actually the biggest indicator of someone's personal risk on the road is whether they are likely to have high cornering speeds, not whether they're likely to brake harshly or accelerate harshly. This is the biggest indicator. If you're likely to take a bend at excess speed, then you're a much higher risk of being involved in a collision. What about following distance? We know that that's important too, and there's more and more data available on that. Distraction and drowsiness, it tells you about the person, but does it really tell you about the road? I'm not quite sure that that's the case. So if we think about what I consider to be the holy grail, so perhaps it isn't just more data. I would really love to see access to manufactured vehicle data. There's a treasure trove of information in there about how vehicles are being driven, what safety measures are being deployed. Wouldn't it be great to have a map of our cities to see where AEB is being triggered? That would really tell us a lot about pedestrian and vehicle interactions. It does require a lot of partnering, but I think this is something that we're going to be coming on to later. There's so much potential in the data there. How can we unlock that, and more importantly, turn it into something that's useful for practitioners at the end of it? Now, unfortunately, we have run out of time, so we don't get to talk a little bit more about our project Rapier, which does have a few things in common with the AI wrap approach that we heard about yesterday. It's a lot earlier in our development, but it's some of the same things about taking in geocoded data and visual data sets and other things like that. Something that we're hoping that we're going to be able to continue working on. But it's on there, and there is a link to a video within our slides, which I'm sure you've already seen distributed. Okay, I think that's all from us. Thank you very much.